So welcome back to Software Engineering for Fall Methods, and Happy New Year to everyone. So the first lecture this year is starting our last chapter. We had one chapter on SAT solving. We started with this propositional logic, and then we looked at SAT solvers. Then we looked at first order logic and SMT solvers, extensions with theories like integers and other data types, things like that. And then we looked at alloy, which is a relational first order logic, so a special kind of first order logic. And now we're going to look at something, again, different, at something called modal logics, or a specific one out of these logics with different modalities is temporal logic. So we'll have a look at what temporal logic is. But first, maybe some little bit of reflection. You don't have to do it online because we can just, it's such a small group that we can just discuss here. Like what kind of problems could we solve with a SAT solver? What would we encode with a SAT solver? What are the kind of real life problems, or what would characterize problems that we can solve with the SAT solver? Boolean expressions, everything we can kind of translate to, well, propositional logic. Yes, that's what the SAT solver does, right? So everything that's Boolean, so things that don't have maybe complex data types, like integers, this would probably not be a good choice. But we could also do other stuff. I think this role-based access, for example, there we had a bit more complex things because we had tables, and we already started having things like relations, right? We had relation between a role and a capability. So already those things, maybe they stretch a bit what the SAT solver can natively encode, but it's still quite simple to encode it also with a SAT solver if the relations are not too many, if they don't get too complicated, the values that they can have. And then we moved on to SMT solvers, and there we saw basically that everything we can do with a SAT solver, we can also do with an SMT solver. And what is the additional stuff? So what would be the problems that we can now also handle with an SMT solver that maybe were not nicely handled with a SAT solver? Yeah, data types, integers, arithmetic, stuff like that. The relations also between them, more complex arithmetic. There are some things that do not work well. Polynomials, for example, they usually don't work well with SMT solvers. It depends on the degree of the polynomial, but then sometimes it can get really, complicated. So for example, we tried, this was, I think one of the example projects that I showed was that we can use SMT solvers to analyze models that we learned from machine learning algorithms. And there we looked at decision trees, which are really easy to formulate because the features, they're basically real numbers. They have some values, and then we only have some Boolean decisions. Then I probably didn't show support vector machines, but they're also easy. But then some student also tried to add support for the k nearest neighbors, and there you need to compute distance metrics. They usually involve squares and square roots, or even higher polynomials and roots. And turns out that this doesn't really work with SMT solvers. They will just say unknown. So stuff like that, there are still limitations, but there are limitations in general. So these logics, the first order logics that we looked at with those theories of integers, arithmetic, they are already so, let's say, difficult that there won't be any solver that can handle them as long as that solver runs on a traditional computer. So you need manual effort because the computer, we know that computers as we know them today will not be able to solve all problems that you could express in those theories. Yeah, and then alloy. What was the main difference between alloy? So we looked at this wish list example. This was kind of imitating a SAT solver in alloy, because the elements that the children were wishing for, these were basically Boolean variables. They were either true or not. So this is one particular way how you can use alloy to do what a SAT solver can do. And you can extend that to anything that the SAT solver can do. You can encode it in Alloy. So Alloy is also at least as powerful as SAT solvers. But then we saw that some things are much more convenient to express in Alloy, and those are usually the relations and quantifications. So yeah, other kind of problems that we could solve with Alloy are things that involve more complex structures. So whenever we talk about either software architecture or object models, then Alloy is probably a good choice. SMT could also work with encoding structures and data types, but there are some limitations where then your SMT problem might either get very complicated to express, where it's more convenient to express it in Alloy, which has a much richer language and a more, let's say, purposeful language for structures, because you have joins, you have relations, and you write facts, you write predicates, you write functions. So it's a bit more convenient than writing SMT-lib format. Depending on what you want to do, but there were also some limitations. So what were limitations of Alloy compared to SMT solvers? Integers, yeah. Alloy has integers, but they are always very, very small domains. And if we increase those domains, then the analysis takes forever. And Alloy doesn't even handle real numbers. So in with SMT solvers, so for example, this analysis of machine learning models, no chance, because usually you need real numbers or floats, something like that. Okay, so we already saw SAT solvers, they are like the bottom of everything, and then SMT solvers, they are richer than SAT solvers, and then kind of next to SMT solvers. So we could say that the SMT solvers probably can do everything that Alloy can do. So they also are stronger or more powerful than Alloy, but Alloy is more, let's say, has a nicer purposeful language for some models that we might want to express. Some more domain-specific language that is closer to what people might want to reason about if they want to reason about structures. But Alloy has limitations of the scope, for example, and also has limitations with concepts like arithmetic, which SMT solvers are much better in handling those. And now let's look at some kind of example system and see what would we use to model these kind of systems. So this is a new example, one that we didn't have so far. Let's say we have a vending machine that receives different coins over time. And then we want to check whether the system delivers soda once enough coins are present. So this machine, basically, you can put in coins. And if you have put in enough coins, let's say maybe 3 coins, then you should get a soda can out of the machine. So it's a vending machine. And how would we check that? How would we encode this? This would be one example. And let's look at the other one as well. So we have a traffic light control, and we want to check whether all the lanes will eventually be allowed to pass. So let's say it's a crossroad, and there can be cars coming from different sides, and we want to make sure, we want to check whether that no car has to wait forever. So at some point in time, the car will be allowed to pass. Yeah, so how would we encode this? Would we encode this with SAT? What are some aspects of this that we could encode with SAT? Of any of the two examples? Sorry? We could have some variables that say, like, coin 1 is present, coin 2 is present, coin 3 is present, okay? And then, of course, we can have a variable for soda is delivered, right? So, yeah. But this vending machine, actually, it only has one slot for coins. So, yeah, it would have like one thing that says, well, right now there's a coin edit. Well, we can do any kind of encoding. Okay, let's do an encoding where we say that where we just initially then all the coins would be false, right? Huh. But then how do we model that people are adding coins? Because the system state we would have to model as all the coins are false, right? No, the machine, when it's put there, it doesn't have any coins in there. So that's a bit tricky. Probably we need to relate something that, and also if you have maybe one coin 1 entered, then maybe the coins come in some order. So you can't have coin 3 is already there when coin 1 is still missing. I don't know. Should you have this or should you not have this? Or could you enter 3 coins at the same time? Like from once the system has no coins, can you jump to it has 3 coins in there? I don't know. Usually you can only put 1 coin in the slot, right? So we're missing something in the logics that we had so far, right? It's a bit tricky. And this one, the traffic light control. So let's say the colors of the traffic light, we could do that as well, either maybe data types in SMT or simply Boolean variables, right? And then we would say it can only be green if it's not red and not yellow, right? And then what else might you want to state about some traffic lights? That the cars have passed, okay? Or that the cars are allowed to pass, right? Because that's a bit different, right? You could have a green light and still not drive, which would be really annoying, but it can happen. Okay. So we need something to model this, right? Because it says here cars have passed. Okay. So let's say we have a variable cars have passed. We probably need more than one variable because they can pass on different lanes, right? Let's say we have 2 lanes, and to make it simple, only cars only drive in one direction, but still there's a point where maybe they have to merge into the same. So you don't want both traffic lights to be green at the same time, right? Because otherwise they might crash. But this we can express, right? We can express that green on light 1 implies not green on light 2, and the other way around, right? So that's something we can express. In SAT, in SMT, in Alloy, right? But then how do we say that they are eventually allowed to pass, right? So we could make a scenario where we can say, is it possible that car A on, I don't know, 1 lane passes, right? You can check, is it possible that this variable can be true? Is there an assignment where this car A is allowed to pass is true? Given all the constraints about how traffic lights should behave, that they are only one color at each time and that they are not green at the same time. So we could do a kind of check that the general rules of traffic light, would they allow cars to pass? Is there a possibility to have a car pass? But we can only check it for the first lane, then we can check it for the second lane, but that's independent, right? We don't know whether there is an algorithm controlling the lanes that will actually make sure that we reach those configurations of the SAT variables. Right? We might have, we know we can't reach them at the same time, but we might reach one, and then after some time we might reach another. But right now we don't really have ways to express this relation between the different assignments to the variables, right? We can express traffic lights and allow it to pass, but we cannot really express how they're related to the future or to the next step or to even more steps. So we probably need some different kind of extension of logic. What we're going to, we also need to evaluate this module. Okay, yeah, I think it's only 3 of us, right? So we should still please evaluate this module now. Is it taking long? Do you want to do it at home? Are you going to do it at home? If you all promise me to do it at home, then Yeah. Okay. So, or I'll post it on Moodle, but usually the problem. So the problem is if there are, I think 5 is the minimum people who have to evaluate it. Um, if it's less than 5, the statistics are simply deleted without anyone seeing it. So if it's less than 5, I'm never going to know how this module has been evaluated, and I think nobody else in the university will know. So it's really important that we get enough people to fill this out, because otherwise, yeah, we're not learning how to improve. But yeah, let's continue. I think it's more interesting now to get more content done. Also for the recording, some people might be watching the recording. Yeah, so we're now going to look at a new language to express those things that we encountered in those 2 examples, and of course many more. This 4th language is here. Up here it says LTL, and that's we will see what this LTL stands for. Just as a remark, there are ways to encode these things in, for example, SAT solvers and SMT solvers in limited ways. And there are ways to encode them in Alloy as well as direct elements of the language. So this new logic that we're going to learn here, 2 years ago, people put it into Alloy as well. So we didn't use it yet because we didn't know this logic yet. But this logic that we're going to look at, people have integrated it into Alloy. So you can do stuff that we will do here at the logic level. You can also do it in Alloy with maybe some restrictions, some different wording, because Alloy is very specific. So this logic that we're going to look at now, it will be based on propositional logic and extended. And Alloy, of course, is not a propositional logic. It's a first order logic. So it's more rich than that. So they needed to do maybe some slight modifications. But this logic is also integrated in Alloy. And we will look at a different tool than Alloy because this different tool makes it a lot more explicit what this language is, and it's a bit more powerful. So we will also have a new tool for this kind of logic. But first we need to introduce this logic, and this logic is called temporal logic, but there are many variants of it. In general, temporal logic is simply a logic where we can represent propositions and we can qualify them in terms of time. So propositions, this was our usual propositional logic. So we just have Boolean variables and we can talk about them in the usual way as we did in chapter 1. But now we can add aspects of time to this. So we can add a new kind of dimension of time. Which means that these formulas, they are not really just statically true or false in some model. And we will see exactly what this means to evaluate a formula on a model. But now models will actually contain states that represent some kind of flow of time. And a formula, like a propositional logic formula, could now be true in one state and then false in another state. And well, that's fine for this logic. We will see how we can actually use that to say that something is sometimes true and sometimes false. So if we think back about the traffic light, then that the car on lane A is allowed to pass. This must be sometimes true, because we said eventually it should be true, but sometimes it must be false because the other car needs to pass, right? So that's how at different times the evaluations might be different. So this logic will consist of Boolean operators and then temporal operators. And here it says temporal logic, but there are actually many temporal logics. So you might come across many. There are some which are, let's say, the most popular, and I picked what I think is the most popular and the most useful that you will encounter in most applications, and that's linear temporal logic. And we will look at some, well, not very deeply. There are some distinctions. So, for example, there is a model of time which is linear, which means that every point in time has one successor. So you think about time as progressing with one step at a time and only one, well, yeah, successor at a time that you reason about. But then there is another one where you have a branching time. So where you could not only say that in the next state something happens, but you could say there exists some next state where something happens, and there are other next states which right now I don't care about. So this would be the branching time where you could, so and time in general, we know it could take different outcomes, right? And that's also true in the linear time. But the idea is that in the linear time, we evaluate our formulas over one particular outcome or over all of the particular outcomes. And in the linear time, this is kind of implicit. We can't really change the way that we're evaluating them over a linear branch or a linear flow of time. But in branching time, we can really make this explicit. In our operators, we can say, now I want to say something that needs to hold for forever from now on, or I want to say something that needs to hold forever in some futures from now on. So stuff like that, this would be possible in branching time. In linear time, it's more simple. We don't have that obligation to say whether we want one existing possible future or all futures, stuff like that. In linear time, it's we don't have to explicitly say it. And there are some things, of course, then we cannot say in linear time, because things like in branching time, where we can say there exists some possible future where something happens, we can't say that in linear time. Or not so easy, not directly. So then there is discrete versus continuous models of time. Anybody ever heard of this, what this might mean, discrete time or continuous time? So this, you could imagine this as discrete time, you usually use some clock ticks. And you're only interested in anything that happens at a particular tick of the clock. It's like a CPU that works at particular ticks, and it can only compute in each, let's say, tick of the CPU clock. Then there is also the continuous model of time. That's usually when you have physics involved. So every system that you want to control that is not a computer system, not a pure computer system, this has some continuous model of time where even between between any 2 points in time, there are further points in time where something might have happened. And then usually for computer systems that you want to control physical processes like cyber physical systems, everybody heard of this term, cyber physical systems? So that's also I think it's maybe also often related to this industry 4.0 because there you're trying to control manufacturing processes, and you're trying to control like physical processes with machines, with computers that you can easily reconfigure. So this stuff mixes the discrete of the computer and the continuous of the physics. So if you have some kind of like this, those segways where you can have two wheels, you stand on it and then you just drive like that, or those hoverboards that were called hoverboards but are not real hoverboards. So those would be examples of cyber physical systems, because you have some physical process, you have gravity and people moving, and you have a discrete process where you have some kind of controller that needs to make sure the physical process remains stable, that the Segway doesn't tip over, or that this hoverboard doesn't tip over, which it can only do in some limits. But that's basically some examples where those two are mixed, and that's always getting a bit tricky. Because usually what you do is you need to sample measurements of the continuous time in the discrete time, because you have some CPU running, some microcontroller, and then it gets a bit tricky. And then there's also point-based versus interval-based temporal logics. So point-based is you have basically one thing happening at one time, but interval is you could have multiple things happening between time steps. And you can combine these, so you can have, in discrete ones, you could have a sequence of events that could have happened in this interval between the discrete points. And then in the continuous, of course, you can imagine that there's intervals implicitly. Anyways. And we will look at only one thing. We will look at the linear one with discrete time and point-based. So the ones that are highlighted in blue, those are the ones that we will look at in this logic. So yeah, let's look at maybe the next question. What model of time would you prefer? So there's like it's a bit like a religious war between linear time and branching time. So there are like communities where they say, oh no, branching time is the only real time that we should use, and the other people say, no, linear time is the one that we should use. And yeah. Yeah, so I also have a set of slides about the branching time, because there's basically this LTL, linear temporal logic, and then the CTL, I think, computation tree logic. Those are both linear, these are both temporal logics. And yeah, I think we will not have time this semester to go over CTL, but that's basically the most competing, the first two, linear time and branching time. Those are the ones that are both, the most relevant, let's say, to understand. And we will focus on linear time. So I prepared you well for saying, yeah, linear time is the best. Okay, good. Everybody agrees. Very good. So this linear temporal logic, this was actually introduced a very, very long time ago as a logic. So back then, people were thinking about, well, how do we actually express these temporal relations between different system states? And then they introduced this in 1977 as a logic. And then soon people started to see, well, how do we actually use this logic to evaluate it over systems? And then a lot of work was done in this area called temporal model checking. So if you see someone say talk about model checking, then usually they mean temporal model checking, and that's mostly based on this LTL and CTL logics, where the CTL is this branching time logic, the computation tree logic. So the extension of propositional logic is basically that we have some operators, some connectives that allow us to refer to the future. That was introduced in this the temporal logic of programs. And now, of course, we have to give some model of time. How do we model time? And you can model time simply as a sequence of states. So we see that's the linear time. It's like a list of states. It's also often called a computation path or simply a computation. And the, interesting thing is now that it extends infinitely into the future. So why do we need it to extend infinitely into the future? It turns out that it makes things a bit easier to assume that things are infinitely extending into the future and not just finitely, because if we think about the traffic light system, how many, let's say, elements would you want the sequence to have for the system to work perfectly? Maybe 100 cycles of switching between different light phases, or 1,000. I don't know what each cycle is. Maybe a cycle is a few milliseconds. But basically, you would want the system to run until, well, somebody turns it off, right? So you would, and you don't know when somebody will turn it off, the traffic light, or the vending machine, or any other kind of control system. So that's why we simply assume that it runs infinitely long. So we simply say, well, it runs forever, although very likely we cannot build a computer that runs forever, but yeah, we will just assume that because it makes things a lot easier. Then we don't have to handle any corner cases of what happens at time slot, I don't know, 20,000. Will the system stop or not? We can just say this time sequence simply extends infinitely into the future. And the main ingredients of this logic are, again, a set of atoms. They are called often atomic propositions. So they're like our Boolean variables. They're like in propositional logic, our atoms that we had there. They can be either true or false. And here, the significance of them, now that we have states, because we now have a sequence of states, we simply say that these atomic propositions, they are either true or false in states. So for each state, we will decide, are they true, are they false? And this is the kind of way that we model the time. So with our traffic light, in each state, we would say whether the first traffic light is green, is it true or false? And in each state, we would say whether the second traffic light is green, true or false. And then we would have some, of course, constraints, so that we would say for each state, the two lights are never green together. And that's something we could evaluate then over this infinite sequence of states. And yeah, of course, the tricky bit is how do we evaluate whether something works for an infinite time into the future? And there are some issues with evaluating that. So we need to give a meaning to this logic so that we can actually evaluate it. There are different ways that you can define this. And we will see one that is, yeah, the most commonly used in practice, so that we can actually check these constraints. The way that we build these formulas are, well, there's of course the true, then there is a variable, so P is any kind of atomic proposition, so that's just a normal variable. Then we have negation of any kind of formula. Then we have disjunction, any kind of formula or another formula. And then we have, those are the tricky ones. Those are the ones that refer to time. So this X refers to psi. So X psi means that something happens in the next state. So if we state this at the beginning, then it means that at the second step, or at the next step, this formula must hold. But currently, it doesn't need to hold. But in the next one, it does need to hold. And then there's until. So now we only see two temporal operators, and we also don't see conjunction. We don't see and. We only see or and negation. But that's usually used because you can represent conjunction just by negation and disjunction, and you can represent further temporal operators. We will look at some of them also as abbreviations of next and until. So the U is for until, and yeah, how do we model the systems that we want to check such an LTL formula over? We need to give, well, a way to kind of specify system, because we want to describe the behavior of our, let's say, traffic light control or of our vending machine. And the most common way is to use transition systems. So we have states and we have transitions between states, and the states, we will simply label them with our atomic propositions. So in each state, some variable is true or false, or all of them are either true or false. They have some value in each state. And then there are transitions that say which states can we move to what other states. So for example, in the vending machine, if we have no coin inserted, then we can maybe move to the state with one coin inserted, but we cannot directly move to the state with two coins inserted. So these would be the restrictions on transitions and states. And then we can interpret those formulas, those LTL formulas, over those systems. Right? You could imagine that you can implement the traffic light control using some states and transitions. You can move from a green light to an orange one, and then to a red one, and then the other side, after the first light is red, the other side can show the the orange and then the green, and so on. So we will now look at a bit more, let's say, mathematical details of how we're going to interpret formulas, LTL formulas, over states and transitions, because for that we need to look at those computations or those paths. We need to write them down, what they are, and we need to make a bit more explicit what's the structure of our transition systems. So a transition system has a set of states, then a set of transitions, and a set of labels. So these labels are simply telling us which variables are true and false in which state. And well, the transitions, they tell us from what states can we move to what states. So here you see that this L is a labeling function that takes a state and gives some set of atomic propositions. And this subset of all of the atomic propositions is basically those that are true in that state. So maybe we can do an example with our traffic light. So, well, it's a transition system, so let's start with a state. And let's say here, well, what are the variables that we have? So the atomic propositions, let's say we have like a very much simplification, green 1, green 2, maybe just those two, right? That's very, very simple, maybe traffic light. So we have some lane here, and maybe some lane here, and they all want to drive, let's say here. And then this is a green 1 and a green 2 traffic light. So now these are roads, right? And then some car might come here, and if green 2 is green, then it can go. So we want, for example, we would like some stuff. So let's say we need to start in some way. So let's say both are false. We have not green 1 and not green 2. Now, when we looked at this on the slides here, it says there's a labeling function, and it says it is a subset of atomic propositions. So I now wrote a formula that's not really a subset, right? So as this label, the label of this state would simply be the empty set, because everything is false here, right? Yeah, so I'll put this in parentheses. This is what both are negated. This basically means the number of atomic propositions that we label this with is the empty set. Nothing is true in this state. So now let's say which traffic light should we make green first? Let's say this one, right? And then afterwards, maybe we can, go back here. This would be a transition system. These are the labels here. Nothing is green. Here, this traffic light is green. And then we can move around those states. And every now and then, so every second state, basically, the first traffic light here would be green. What about the second one, G2? It's never green. So here, in this transition system, this would only just turn this on, turn it off again, turn it on, turn it off again, and this one, it would always remain off. Okay, it's safe. The cars will never crash because both lights are never green together. But maybe there are some issues with this. Maybe it's not the best implementation. Okay, but that's basically a transition system. That's how a transition system looks like. Those, circles, they were the states. The transitions, we have two transitions that are a relation between states. So we have, this one is a transition where it says we go from state 0 to state 1, and then we go from state 1 to state 0, right? We can give them names. Let's just give them the name. This is state 1, this is state 2. So our transition relation would be, we can go from, now it's a set of pairs, S1 to S2. That's like the relations in alloy. And then we can also go from S2 to S1. That's our transition relation. Our set S is the set S1, S2. That's just a set of states. What else did we need? We needed this labeling function. Well, the labeling function would, basically the labeling function would, how do I write this function? Okay, let's say L of S is for S equals S1, and it's, they're always sets. And the label is this green one for S2. Okay, this would be our transition system. And here we have another one. We have three states now, and we have P, Q, and R as atomic propositions. And it's very much the same. We have here S0, S1, S2. There are some transitions between them and some loops. Okay, and now we could basically write down these relations here very easily. S0 goes to S1, that's this transition, that's the first tuple in this relation. S0 goes to S2, that's this arrow. So it's just a different way of representing this. And these transition systems are now what we want to evaluate our LTL formulas over. Now, we said that we want to implement time as a sequence of states extending infinitely into the future. Now, is this possible in this transition system? Can we always extend our sequences of states infinitely into the future? So we can, does anybody see an infinite computation in this transition system? So let's do the first thing, the easiest. Is there an infinite? Yeah? S0, S1, and that repeated infinitely many times, right? We can go from S0 to S1, and then we can go from S1 to S0, and we can do that as many times as we want. Yes. So this way, basically, that thing is infinite. We can also do larger cycles here, S0, S1, S2, S3, S1, S0, and so on, and any ways to mix them. But there are some cases where we cannot extend into the future anymore. And that's in which state? S4. Yes, S4. These are called deadlock states because this is where the system has no further way to progress. So it's a deadlock. This is in parallel programming. You might have heard of these kind of deadlocks where you have two processes and they deadlock because they're waiting. Each is waiting for the other, or even more processes are waiting for each other, and they will never finish. So here we have a deadlock, and there are some easy ways to deal with deadlocks. One, or the most common, the way we simply deal with deadlocks is we add a special deadlock state that from every deadlock in the system, you go to that special state and you can stay there forever. So it's like a marker state that says, yeah, we are now in a deadlock state. So you give this, you add a new state that is the deadlock state, and every deadlock state from the previous system will have a transition there, and it will have a transition to itself. So now, if you ever end up in S4, you can still extend infinitely into the future by simply repeating SD, this deadlock state, forever. So this way, we kind of fix the system, and every possible computation in this system now can be infinite. We can always have a way to extend this infinitely from any state that we could be in. We can never go back, but that's the point. We still need this information. Yeah, this was actually deadlocked. Something bad happened there. Okay. Now we can define path. A path is simply a sequence of states. So we go through our transition system, and in each way we continue. So we pick a state. That's our state that we begin with, and then each next state has to be a possible transition. So here, this arrow here means that we have a transition from this state to that state. From every state to the next state, we have a transition. So yeah, what would be a possible path here? Let's say we want to start at S0. Yeah, do they have to be infinite? Yes, so they already have to be infinite. So you just need to cycle around. So here, S0, S1, S2, S0, and this infinitely long, that's a path. What, let's say, sequence of states would not be a path? What infinite sequence of states would not be a path in this transition system? So the path requires us that between consecutive states we have a transition. So simply if we say S0, S3 infinitely often, then that doesn't work because there's no direct transition between S0 and S3. So this would not be a path. Or S0 repeated infinitely often is also not a path because from S0 we cannot go directly to S0. We have to take another transition. Here, SD infinitely often, this would be a path. That's fine. So that's, a computation, a path, a computation, that's kind of synonymous. But a sequence is not enough because a sequence could have states that are not arranged based on transitions, right? So not any sequence is a possible computation by this. This thing can only generate computations that follow the transitions. So that are these valid paths. Okay, so now we have path, and we usually write a path either as pi, then we can write S1, we could write them comma separatedly like here, or we can write the arrows so that it's clear, yes, there's really a transition required. And once you have a path, you can also take a suffix of the path, and that's again a path. So a suffix simply means we, instead of starting at the first state, we start at the state I. So we could start at the fifth state or the sixth state. So if I have a path and I cut off some prefix of it and only look at the suffix, is that still going to be a path? Why? Why is that still being a path? It's an infinite sequence, yes. So it needs to be infinite. But if we cut off some finite number in the beginning, it's still infinite, right? If we cut off the first 5 elements, then the remainder is still infinite. Okay, and then every successor needs to respect this transition relation, but of course it did before we cut some stuff off, and then it still does afterwards, yes. So any suffix is, again, a path. Okay, you could imagine unfolding a model as some kind of infinite tree, right? Because how do we construct path? Let's say we are at this state S0. what are the possible paths we could do from here? We could go to S2, right? Or we could go to S1. So there are multiple possible successors here. We could go to S1 or to S2. And then in S2, well, we can only remain in S2, right? So this kind of is a very simple continuation, but in S1, we still have the option to go to S2 or to go back to S0. So in S1, we could go to S0 or to S2. So it's basically you can unwind a transition system as some kind of infinite tree. And again, it's only infinite because we are deadlock free, right? Because we don't have, it always has a successor. Every state has at least one successor. That's why this tree also becomes infinite. And then every way that you can go through this tree, that's basically a computation. Yeah. Now, how do we relate these paths, these computations, to our LTL formulas? So very simple. If we have the LTL formula true, that's the most simple LTL formula we can write, then this is always the path always satisfies this formula, always models this formula. So the path, any path models the formula true, right? Because true doesn't have any requirements. Then here, the path where we have to satisfy the proposition P, this is the path basically satisfies this formula that is only one single variable if that variable is true inside the first state of the path. So let's look at our example system here. Let's say we start in S1. Can we do a path in S1? So some path, I don't know, by A could be, we don't have many options here, right? We start in S1, then we can go to S2. And so on, right? We're going to write all of it. And then let's look at the second one. How many possible paths do we have? Let's look at a second one. Second one could start in S2. Okay, so maybe this transition system is a bit boring. Not many things going on here, but now let's look at the formula. What LTL formula should we look at? Let's say, well, we need some proposition, right? So let's look at G1. Now, the question is, does path A satisfy G1? Does path B satisfy this G1? Does path, let's do a few exercises here. G2, path B satisfy G2. Well, I mean, that's basically all of our propositions that we have, right? We can't do more checking of single propositions. So this is an example of, that's an example of this second bullet here, right? So we have a single atomic proposition, and we want to check whether the path satisfies this formula. So this formula here, it's an LTL formula, right? This is the single proposition is an LTL formula. So does path A satisfy this G1 formula? What we need to do is, because there's no temporal operator, so this means this formula only applies to the initial state. And now we look at the initial state is S1. S1, does it contain the label G1? No, the set of labels is empty. So this one Does not. Now, the second trace here that starts with S2, does it satisfy the G1? We look at S2, the initial state. Now S2 is the initial state. It has the label G1. So yes, this does satisfy. So yeah, that works. Now, does this path satisfy this formula G2? No, because anyways, there's not a single label in the labels of the first state in the path pi a, so it doesn't. And now this pi b path has S2 as the first state, and that also doesn't have G2 as the label. So that's how we would evaluate single individual Boolean variables or atomic propositions. Okay. Well, negation of some formula, that's simply the path doesn't satisfy the formula itself. So that's very well, yeah. So if I'm asking whether pi a satisfies not G2, then that is correct, because the negation of not G2 is simply G2, and we know that that is not satisfied. So this basically negation of a formula simply means that the path does not satisfy the unnegated formula. Okay, very straightforward. Or is very similar. Right? If we say it satisfies that or that, then we simply take each one and check does it satisfy this or does it satisfy that. So very simple, straightforward from the or that we are used to. Then next, now this gets a bit more interesting, because now we're actually looking at the time. So with next and then a formula, we simply check whether the prefix starting only at the second step does satisfy that formula. So if we would go back to here, so if we say pi a, does it satisfy next G1, pi b, does it satisfy next G2? Then we can also write this as okay, that gets too confusing. Let's just directly evaluate it. So if we say next, this means we look at not the first state, but the prefix after taking the first state off, which is now S2. And now we look at the labels of S2, because now we're back at something we can decide. We look at a single proposition, and that's stuff that we know. We simply check whether it's in the label. So S2, the label of that is G1. Yeah, so that thing is actually satisfied. And this thing here, if we look at this trace starting with now S1, S1 doesn't have any labels, or has the empty set of labels basically, and then it doesn't have G2, so that's not satisfied. So with the next, we're simply asking in the next element of the sequence, if we ask the next here, then it's basically we look at, is the formula true in that thing? So it's simply, taking a prefix. And then until, that's the most complicated. This is asking whether some formula holds until another formula holds. So does psi hold up until phi holds? So we say there must exist some state where the formula that we want to hold, here eventually on the right side, the phi, where that actually does hold. So the until says this thing must happen. The one on the right side must eventually be satisfied. That's what the until requires. So the one on the right side must eventually be satisfied at some index I of our computation. This index could be 1. So it could be the very first state. So, and then for every smaller index j, this formula on the left side, the psi must hold. So it's basically this formula psi will be true until eventually phi is true. So yeah, in our example here, and our example is really, really simple. So we could write, but we can still, yeah. So let's extend this. You still need to see that, right? I need to see the labels. Yeah, I'm going to write here. Okay. So does pi a satisfy? Now, yeah, we need a formula with until. We can take any formula, but let's take a simple formula. So we could take a formula G1 until G2, or we could ask. Yeah. True until G1. Okay. So now, what do we need to do to evaluate this until? We need to see, does the right side ever happen in our computation? So in pi a, in this path, do we ever see a state with the label G2? So, sorry, yeah, G2. We don't. So this means there's no way that A satisfies that. So this is not satisfied because already the first requirement that this G2 needs to be satisfied didn't happen. So this until is not satisfied. Yeah. Now the second one in B, is there any state in B where the G1 is a label? So let's go back. It starts with S2. S2 already has the label G1. Great. So first criterion, yes. So this thing happens. That's very good. And for every state before that, do we satisfy true? Yes, true is always satisfied, right? Any formula, any path satisfies true. So yes, this one is satisfied. Would it also be satisfied with pi a? So pi a starts with S1. We don't see the label G1 in S1. Okay. But we see it in S2. So this means that now our index I would be 2. And we see that this thing is going to happen. That's great. Now we have to check that for every index j less or equal to I minus 1, so it's less than I, so j less than I, right? And there's only one index that is less than 2. That's the index 1. And does this true hold in the state? Yes, of course, because true holds in every state. Okay, so this one is also fine. That's the until. Okay, so two temporal operators, the next and the until, and we know how to handle them. Now, let's look at some more examples. So we could label these sequence of states, and then we say here, this proposition or this atomic proposition P is actually a label of S3 to S8, and Q is a label only of S9. So now let's look at the path starting at S2. It satisfies next P because the next state is S3, and there we have the label P. Okay, same. And then the path starting at S3 to S9 satisfies P until Q because, well, does Q ever happen on this path? Yes, it happens here in S9. And then in everything before that, now only if we start here, so in everything before that up until S3, did P hold? Yeah, in every single state, P was holding. So that's, yeah, P until Q. P until Q doesn't hold from S1, right? Because Q eventually holds, yes, but in all the indices before, not in all of them P holds, because in index 1, P is not true. So this means the path starting from S1, we would not have P until Q. Okay, good. There are some additional operators, and they're simply defined based on these. So f psi, eventually psi, this is the operator eventually. It's simply true until psi. What does it mean? This means that basically we only require that there is some point in the future where psi holds. And until then, we don't care, because this true basically means we don't care. So this means at some point in the future, we will see psi, and that's defined as this until. And then we have globally. That's really ugly, but yeah, not eventually, not psi. What does that mean? If we say eventually not psi, this means that at some point in the future, psi will be false. If that doesn't happen, it means that psi is never false in the future. So psi always holds. That's the globally. Globally is always. So psi always holds. So what would be a nice property for our traffic light system here that we would express with globally? What would we always want to hold on our two variables? So is there any temporal property for our traffic light system that we might want to say with globally? So we might want to say globally, well, G1 is not G2, or yeah, something like that, right? Globally, well, it's a bit easier. We can also say globally, not G1 and G2. So we don't want both traffic lights to be green at the same time. So yeah, globally not this. Okay, and then is there anything we would want to say with eventually? We could say something like eventually green 1, and we could say eventually green 2. So this eventually green 1, we can look at this transition system and see no matter which state we start in, that's satisfied, because we will always end up in a state that has the label G1. This G2, we know it's not satisfied no matter where we start. We never see the label G2, so that's not satisfied. But actually, sometime in the future, G1 just means that at some point, our traffic light system will have to turn the light G1 to green. So that's not really what we want in general, because this means that it's fine if the traffic light was green once, and then in the future, we don't know what happens. So it could turn green once and then turn off again. That would still satisfy eventually green 1, because it was green once, but we want something stronger. So we want that always eventually green 1. So at any point in time, after some finite amount of time, we want to see the green light again. So that's a bit stronger, because we wrap it. So you can also nest these operators, because we defined the semantics of the operators always on LTL formulas. So it gets a bit more complicated to unwind these definitions, but yeah, that's nesting is one of the powerful features of linear temporal logic, so that you can say always after some finite amount of time we want to see a green light again. And then again, here there's no way to avoid this green light. So of course, this formula is also satisfied no matter where we start our path. So for the two paths that we could start, the pi A and pi B, they will satisfy this formula. And the second formula, of course, still not. Okay. Yeah, so that's then the model satisfaction. So far, we looked at a path and the satisfaction of the formula. Now we can look at the model and the satisfaction of the formula, and we will usually look at a model and a starting state. And then we will require that it's for every path that starts in this state. So no matter which way we construct a path from that state, this path will satisfy the formula. And then we say that the model satisfies the formula. So yeah, the two examples that we had, we could ask, for example, whether our model here in state S1, does it satisfy globally, finally, T1? And then we would have to check what are the possible paths that start in S1. Well, that's very simple because we only have one possible start path here. So we only need to check whether this one path satisfies that formula. Yeah. Now here we have our example transition system again, and we will look at some other formulas. So in S1, do we satisfy the LTL formula P and Q? So this means starting from S1, the first element in any possible computation, of course, is this state S0, right? And it's labeled with P and Q. So this means that this formula here is satisfied. So although we're now asking for all the paths that start from S0, but if we only look at the initial elements, then that's very simple, right? It gets a bit more complicated when we look at the next element, because then there might be multiple next elements that we would have to consider. Okay, let's look at, again, this one, not R. So starting from S0 in this model, all paths, do they satisfy not R? Yes, because R is not present as a label in the initial state. Very good. Now, starting from S0, all paths that we can construct, do they satisfy? Well, here it says, do they not satisfy next Q? So let's see if it satisfies it. So what are the possible next elements? Now we could have more than one path, right? Because one option is to go here and one option is to go there. So is there a path that satisfies next Q? Yes, that would be the path going from here to there. But it has to hold for all paths. So also going from here to there. And that's not the case, right? It doesn't have the Q. So that's why this is a correct statement as well. Then next, R and Q. Yes, all paths from S0. So let's start here. What are the next states? This one, does it satisfy Q and R? Well, R and Q, yes. This one, does it satisfy Q and R? No. So this one is not. Because all paths starting from S0 would have to satisfy this formula. And we found one that doesn't. So if we want to disprove it, we have to find a path that doesn't contain it. And we will later see that this is a very, very powerful way that the tools also work. They will compute a path that doesn't. And this is what we can then work with. Okay, so there are some very common formulas like this globally finally that we already saw, like always, eventually, we want a green light, right? This is some very common thing that many people write. And then there's also, well, the globally with a nested eventually. So this is called the response pattern, that after some finite amount of time, the system will always give a response to a request. So globally, at every point in time, if a request comes, then it is eventually answered. So of course, what you put here as request and acknowledgement, these are just some variables or even subformulas. But this is also a very, very common thing. The reason is that you usually don't know after exactly what time it will be handled. You cannot just say then in the next state. So if you press the elevator button, you cannot say that in the next point in time, the elevator will be there. But you would want to say that you're not going to wait forever for the elevator to come, because eventually, after some finite amount of time, it will come. So that's stuff you would do with this response pattern. Yeah, then simply some safety formulas that you can never get to a state where the system is started without being ready to work. We had another safety property where we said, well, we never want to get to a state where the two green lights are on at the same time. So, and this is a very common way to express those properties. And then this one here is eventually globally deadlock. This is a property where it says after some finite amount of time, we're going to get somewhere where we will stay forever satisfying this formula, deadlock. So you can also nest it this way. Here we nested it the other way around, and you can also nest it this way around. This means that after some finite amount of time, you will stay there forever, and this means that forever after some finite amount of time, this will happen. So these are very, very different, because this thing usually say that something good will happen infinitely many times. So this always after some finite amount of time, this means infinitely many times, because our time is infinite. And if always after some finite amount of time something has to happen, then it means over the runtime of the system it will happen infinitely often. Okay. So yeah, and you can also, of course, write connectors between those operators. So you can say if infinitely many times the system is enabled, then infinitely many times the system is running, as a kind of consequence of if people always press the enabled button, then it should always be running. Or here for this elevator, now it's all nested in the globally. So at any point in time, this is an implication now. So if we are in floor 2, the direction of the elevator is up, and we pressed floor 5, then we will keep on going up until we reach floor 5. So this is like the that it will really go the shortest way just by going up and not go down or something in between. So this in between, so until we reach floor 5, this is this until pattern. Okay. And some other formulas globally. Now this is a thing we have to evaluate for every single state in all of the possible computations starting at S0. Do we have not P and R? So how do we do that? We look at the states, and well, we should actually only look at the reachable states, but we know we can reach all states, right? So do we have P and R together in any of those states? No, P and R, we never have them. So never P and R are together in one state. So this one is satisfied. Yeah. Next one, globally R. So we start in S2. Every possible state that we can, every computation that we can do, every path, well, there's only one path, that the one that stays in S2 forever, and this always has the label R. So yes, this one is also satisfied. If we started in S1, it would not be globally R, because already in the initial state, R is not there. So S1 would not satisfy this. Okay, now what happens if we look at all states? Do they satisfy that eventually not Q and R implies eventually globally R? Now that's a bit more tricky. We could check from which states are we going to reach this state, because that's basically is this ever the case? So from S2 we could eventually reach that. Okay. So and then would that also, so this means this one is true already in state 1, right? Because in the first state already R is there. So yeah, and then do we eventually globally have R forever? Yes, that's true, right? Because R is forever anyways. So also after well, 0 steps, it's already true forever. What about S0? So in S0, is there, if a computation reaches a state like that, what states? Now it's important because there are multiple computations, right? And we need to check it for all the options. So if the computation ever gets to S2, we know it works, right? So this means if the computation ever gets to S2, yes. Is there another way to satisfy this one? Not Q and R. We know S2 satisfies it, but is there another state that also satisfies it? S0 no, it doesn't satisfy R. And S1 doesn't satisfy not Q. Okay, so this means that if we never get to S2, the computation path that avoids S2 will have this one always false, and the left side of the implication false makes the implication true. So this means that either we avoid S2 or we go to S2. And if we go to S2, then the right side is automatically true. So yes, this one is even satisfied from all states. Yeah, now here globally finally P implies globally finally R. So let's see what computations from S0 could have P satisfied infinitely many times. How do we satisfy P infinitely many times? We have to go in some loop that visits a state with label P infinitely many times, right? So how many loops are there that visit P infinitely many times? There's only this one loop, right? Does this loop also visit infinitely many times a state with label R? Yes. So if we stay here forever, then we also visit the R forever. So this one is also true. This one, yeah. And here, S0, globally finally R implies globally finally P, but the negation. So let's see, do we find, if it's negation, we might find a counterexample, right? So we might find a trace that doesn't satisfy this. So that's good, because if we have the satisfaction, we need to look at all paths. If we have the negation, we need to only find a single one that might violate it. Okay, so globally finally R. How many ways are there to get globally finally R? There are two ways, right? We can move here, but then we stay here forever. Or we can go in this loop, or we can go in this loop and then go out here. And do all of them satisfy that we get globally finally P? No. Can you give me a computation that starts in S0 and does not satisfy this? Yeah, S0, S2, and then S2 forever. That doesn't satisfy globally finally P, but it satisfies globally finally R. Yes, so the last one is, well, the last statement is also correct because it doesn't satisfy that formula. Okay, very good. We're out of time, right? Okay, so yeah, if you can do the evaluation, the lecture evaluation at home, I'll also post it on Moodle, but you have the PDF of the slides anyways. And then see you on Tuesday. Okay, and we will do, there's one thing, we will do a help session for the projects. So we just updated the Moodle schedule. Let's see. I think it's on the 16th, we will do a help session. So yeah, 16th, that's basically, yeah, on this Tuesday, you will have a chance to ask questions about your project, get some advice. If you have some ideas of how do you solve it, we will be here. We will probably have some calendar where you can book a slot so that you can ask your questions. Yeah, okay. Good. So see you next week.